This is Physics 2212 Lab 3 circuits. For this experiment, the purpose is to apply the principles of energy conservation, the loop rule, and the current conservation, the charge conservation. We also need to predict the behavior of the circuits containing resistors in series and parallel. And we need to use multimeters to measure the actual values of conventional current and potential differences in the circuits. We need to examine the behavior of the ohmic resistors and capacitors. In this experiment, we apply physical principles of Ohm's law, capacitance, node rule, and loop rule. For the experiment procedure of charge conservation and energy conservation in series circuits, we first need to construct the circuit in Circuit Construction Kit with two 1.5 volts batteries, one 47 ohm resistor, one 100 ohm resistor, and two ammeters. We predict the current in the circuit equal to the voltage over resistance, which is equal to 3 over 147, is approximately equal to 0.0204 ampere. The actual current we measure in the circuit is also 0.02 ampere. And if we reversely connect the ammeter in the circuit, the current is still 0.02 amperes. And then we need to replace one of the ammeters with a voltmeter. We predict the potential difference around the battery, which is equal to 3 volts. And the actual measurement is also 3 volts. The voltmeter has infinite resistance, so there's no current in the circuit. Then we need to remove the voltmeter from the circuit and close the circuit with a wire and use the voltmeter to measure the potential difference for each part of the path around the circuit. So for B to A, it's 3 volts. For D to C, it's minus 0.96 volts. For F to E is minus 2.04 volts. And for other parts are all 0 volts. Delta V is equal to the sum of the individual potential difference, which is equal to 3 minus 0.96 minus 2.04 is 0 volts. So for the experiment procedure in parallel circuits, first we place an ammeter in parallel with the 100 ohm resistor. Due to the parallel ammeter, the resistance decreases in the circuit and the current increases. So for the calculation to the 47 ohmmeter, for the 47 ohms resistor, which is equal to around 48 ohms. And for the calculation to 100 ohm resistor, it is about 102 ohms. And for the resistance of the wire, it is calculated as 0 ohms. And for the resistance of the ammeter is calculated also as 0 ohms. For the experiment procedure in RC circuits, first we need to construct the circuit with 10 ohm bulb, 20 ohm bulb, 9 volts battery, and 200 millifarad capacitor. So what the bulb will be when it connects to the battery and capacitor in a series RC circuit. The bulb first becomes bright and then dims slowly. And what the bulb will be when it connects to a charged capacitor? It's the same. The bulb becomes bright at first and then dims slowly. So what the current should be in both scenarios? The current first becomes large and then decreases to 0. And measure the time it takes for the capacitor to charge and discharge. So for the 10 ohm resistor, it takes about 9.2 seconds. For the 20 ohms resistor, it takes about 17.8 seconds. The graph shows the experiment data collected for the time-dependent voltage across the charging capacitor. In order to determine the capacitor time constant, We take log of the y component in the previous slide and use it to plot the diagram of the function to time. So from the graph, we know that the slope is equal to minus 0.164. So RC is equal to minus 1 over minus 0.164, and it is equal to 6.098. To check this answer, we use the experiment data so that RC is equal to 30 ohms times 200 millifarad, which is also equal to 6. So here comes the what if questions. First, what if using an actual emitter instead of an ideal simulated emitter? So in real life, the emitter has resistance, thus the readings will not be accurate in real life. The second question is that what if using a real battery to charge a real capacitor with no resistor in the circuit, how quickly would the ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So this won't happen in real life. So though the capacitor is expected to be charged instantaneously, however, since every component has resistance, time is required to charge the capacitor.